Ladies and gentlemen, I want you to look at the general panel model. The first thing we would do in a general panel model is that we are going to now, there are several models we are going to use to estimate this model. And by the way, when we say estimate the model, we are estimating the model to get our parameters, our alpha, and then the beta parameters. Remember, you just see one independent variable, one covariate, but there are several, exogenous variables that are here. The first thing you want to note is that you can use the pooled OLS to run this model. What is a pooled OLS? Pooled OLS ignores the potential unobserved heterogeneity across the groups or across the time. So pooled OLS does not consider there is this lambda t. Pooled OLS does not consider there is this. It only remembers that there is the sample random noise. That's it. It assumes that the effect of each regressor is constant, which may or may not be true. Okay. Now remember, how do you eliminate the unobserved heterogeneity? Remember that the OLS estimator is always consistent, the OLS, on a normal cross-sectional model. When we say it's consistent, what we mean is that the covariance between the error term and the explanatory variables, the correlation between them is zero. So there is no dependency between the idiosyncratic noise and then the explanatory variables. Now, when the error, okay, in a pooled OLS, that situation is not possible. There is a correlation. In a pooled OLS, there is a correlation between the error term and the explanatory variables. And this correlation is sometimes called endogeneity. The reason is because there are other factors, that such as the unobserved heterogeneity, the UI, which should have been part of the modeling, but then is not included in the model. They are not captured, but those factors can affect the dependent variable, but they are inside, hidden, unobserved. They are inside, they can affect the dependent variable. So OLS, if you use OLS, and when we use the OLS, then it is known as pooled OLS. When you use OLS in such a situation with both group and time dimension, what it means is that the OLS is going to be biased. Now, what do we mean when we say the OLS is going to be biased? Now, that's an important word. What we mean is that the expected value of the beta cap, the value of the beta cap, okay, is not going to be equal to the true beta. So there is an unobserved, there is an invisible true value of the coefficient. But this true value, you don't know it, and that is why you estimate it using the betas. Now this estimation, it must match, it must be equal to the true value, but it's not equal to it. Why is it not equal to it? It's not equal to it because you are using a pooled OLS that is not capturing the unobserved heterogeneity. That's the first mistake, and that's called biasness. The second one is that as the sample size increases, so this is a sample size, as it increases towards infinity, again, the value of the beta cap, okay, does not converge to the true value of beta. Okay. Normally, as you increase the sample size, as the sample size gets bigger and bigger, the value, the parameter, remember, this is the one you get from the Excel result, the one you will get from the R results, okay? The true values is not equal to the estimated value is not equal to the true value. So that is the problem. The OLS estimate will be biased and it will be inconsistent. It's no longer blue. Now, let me just give you the principle of what the pooled OLS is doing so that you can appreciate it. Okay. I just want to create a simple diagrammatic representation of it so that you can appreciate it better. Okay. So watch something. Here you have some data called, let's say you have quantity demanded and you have price. And this quantity demanded, you have it for firm 1. Okay. You have it for firm 2, firm 3, firm 4. And you have the data for each one of them. Okay. You have the data for each one of them. You have the data, you have the data, you have the data. Okay. And this data, the information you have here, okay, let's call this section year. And this year, this is the year 1998. This is the year 1998. This is the year 1998 for each of those firms up to 1998. Then you have firm 1 again come here. Firm 1 comes back here. Firm 2 comes back here. Firm 3 comes back here, all the way. And then they also have data on each one of them. Data on prices and data on that. And this is 1999, not 98, 1999, not 98, 1999, not 98, 1999, not 98. Now, the information you have here is made up of 10 firms. The information you have here is also made up of 10 firms. Do you know what Pooled OLS will do? What Pooled OLS will do is that it's going to run this model, okay, and assume that how many firms do we have in total? In total, how many firms do we have? We have 10 firms. Just that the firms appear in the other year. Pooled OLS doesn't recognize the time. You put the time here, Pooled OLS ignores the time. Now, if Pooled OLS is ignoring the time, do you know what is going to happen? It is now going to consider each firm as so to consider this firm as firm 1, firm 2, firm 3, firm 4, up to 10, then firm 11, firm 12. Meanwhile, firm 11 and firm 12 are the same. But Pooled OLS is considering them as different firms. So there is group heterogeneity and there is time heterogeneity. This is the unobserved. This is when Pooled OLS does this, it doesn't take into, now why do we say unobserved? Because the thing is that every variable here, when you estimate the variable, it will have an error. It will have an error epsilon I, epsilon I, epsilon I, okay? And that epsilon number 11 might be correlated with another epsilon. So there'll be a lot of problems for not considering the time dimension, okay? And this is the problem with Pooled OLS. And that is why the OLS, and of course, what it's doing is that it is just pulling the data together and applying the OLS to it. And somebody does that. And that which the person does is punishable, because what it means is that you are going to have a biased estimate. And those biased estimates, together with the standard errors, are what you're going to use to calculate the t-statistic and the p-value. So your significant mean will not be reliable. So Pooled OLS is something that it can work. In some cases, it can work, but doesn't always work like that. Now let's apply the Pooled OLS to our own. Let's use the wage band data to estimate the wage equation for these young men. In the Pooled OLS, we are going to include education and race by the way is Black, Hispanic, and other. Okay? We are going to include them, but they will drop out when we come to the fixed effect model. We'll come and understand how later. So race and education, we're going to include them. These are considered as fixed. Don't forget, we are considering them as fixed. Okay. And then those that are not fixed, the time varying variables. Experience, we are not going to consider it as fixed. We're going to consider experience as changing in the Pooled OLS. We are going to experience square, we're going to include experience square as changing. Remember, we said union is changing. The person's union is changing. And marriage is changing. So a person could be marrying over the period. Okay. And we are going to include the time dummies. Do you remember the lambda t? Okay, lambda t. In case you've forgotten, let me just remind you. So lambda t, we used to have lambda t. This lambda t is going to be, we're going to estimate that also in the model. And guess what's going to happen? We're going to have something like lambda t. Oops. Okay, we're going to have lambda t, and the lambda t is going to be time. So we're going to have beta. Let me just. Aku has taken over my cursor. Okay, so let me just. It's taking over my cursor. I need to just correct it. All right. So the lambda t, okay, this lambda t should be equal to beta 1 and then lambda 1 plus beta 2, lambda 2 plus beta 3, lambda 3, all the way up to beta. Remember, there are 8 here, so beta 8, lambda 8. So we are going to incorporate all the time. These are called the time dummies. They will reflect time trends. They will tell us how the dependent variable, in this case, the log of the wage, okay, the wage rate. It will tell us how the wage rate is changing across time, Okay. So that is a lambda values that we are talking about. And that is the last sentence being spoken of here. Each regression contains a full set of year dummies from D81 to D87. Okay, from D81 to D87. All right, so have that in mind. Now, before you can actually do this, you need to model it. So I'm first going to model the general one, then I'll model the specific one. So under the general model, this is a general model that we know of. This is a general panel data model. Okay. And in this model, the dependent variable, okay, or the outcome variable is a function of the explanatory variables, the unobserved term, the time dummies, which I told you, and then the error term. Now, in Pooled OLS, the whole thing breaks down to become like what you see here. Why does it break down? Because I've told you, it doesn't consider the UI, it doesn't consider the lambda t. It ignores all of them. It ignores all of them. And so all we have, you see, is it doesn't even have t. It doesn't even have t, yi, and then xi. It's just have I, okay, individuals, no time dimension. So we're going to incorporate that into our specification. So in our specification, ideally we should have t here, but we can't have t here because it doesn't consider time. It only sees them as individuals. And so we have education, experience square, union. Look at the way I'm modeling the data. And now I have my error term there. Now, some of the variables are, what do you call it? They are categorical, like ethnicity. So I've just given it a new color. But it doesn't matter because the guy Pooled OLS doesn't even consider them that way. Okay? It considers everybody as it is. Okay, and just models everybody just as it is. And so this is how the modeling is going to be. So if I were to be putting the model in a journal article, this is how I'm going to put the model in a journal article. Then what? Then with this modeling, let us now see how we will assess it. Now, panel models. If a person is forcing himself to still use, because I've already told you that the pooled OLS might have issues. It might have issues, but sometimes it's good. It's good when you do this. If you still want to use it, then you have to correct for those problems we spoke about. Okay. So because the pooled standard errors, the standard errors are incorrect, you need to correct them. And one way you correct them is by using the robust standard errors. This is something we've learned already. The robust standard errors, you juxtapose that against the coefficient, and you will get beautiful test statistics that will allow for cluster correlation. Okay. Remember, that pooled OLS wasn't allowing for that possible cluster correlations. But this one, it will allow. Heteroskedasticity, it will allow it. Okay, it will allow it. And then you'll be able to correct for all of those problems. So we are going to first run the pooled OLS, then we'll run where we are correcting for the serial correlation and heteroskedasticity. Okay, so let's do that in our WHPAN. So let's go to our WHPAN data. This is a model we're going to have. I told you to run the type all of the packages and the models already. So we're going to load the data. The name of the data is WHPAN. So I'm going to load this data into the R. So if you don't have your R opened, please have your R open. This is a data set, by the way. All right, so ladies and gentlemen, you can now see my screen. You can see my screen is breathing and breathing well. This is a panel data analysis. The first thing you want to do in a panel data analysis is to load your PLM package, okay, the panel linear model package. You need to load it. You need to install and load if you haven't installed. I'm assuming you installed. You need to load it. And the command you use to load it is library PLM. Okay. You need to load that package. Type library PLM, and then you load it. Okay, you run that. So I just did mine, and it's showing down there in the console. It's showing down there in the console. I hope it's big enough for all of you. Okay. Now the next thing is to load your data. So when you look at the information content I have here, this is the way you load the data. Okay, I called it WHPAN, so you can call it the same thing. Okay. So WHPAN, and then you use that approach to load the data. So now, WHPAN read.lim, just run this. I'm going to do the same thing. And when you load the data and the data shows, for you to be sure that the data is showing, just highlight it. I've loaded it. Just highlight it. And then you see the data here. And just maximize it. Okay. That's the data set. That's the data set. It's all showing nicely. You can see that the ID is there, the year, okay, the age, the experience, all of the data that I need is here. When you go further, it will show you the other information. The log of wage, this column is indicating the log of wage. Okay. So you have all the necessary information that you need to be able to make the data work. All right. Once you've loaded the data, you can summarize the data. You can summarize it. How do you summarize it? Well, in your, let me go to your slide. In your slide, you will see the command called summary WHPAN. You can use it to summarize the data. Now, I normally do this, even though this is not too important for some, but in most papers, every paper, not in most, you have to bring your summary of your data. I don't know why you want to write your paper and you don't want to bring the summary of the data. So this will help you, okay? So you got to do that. But there's something else you do, which is even interesting. So let me run this summary data. And when you look down here, you will have the results. You will have the results here. I just want to, remember these variables are many, but I just want to talk about just a few of them. So the result I want to talk about is experience. So when you look at experience, the minimum value is 0. The first quartile is 4. Okay. I've already taught you how you can export this to Excel. The median is 6. The mean is 6.5 for experience, and the maximum value is 18 years of experience. So you have all of this, okay? And the information for the others, you have them as well. Normally, variables that are dummy variables, it will not tell you I will not tell you the descriptive statistics at all. Okay? Like this disability, it just tells you the length, and then it will tell you the class is a character and the mode is also a character. Okay, the next important thing you want to note is what I have highlighted, a command known as library parse-text. Library parse-text is an important package that you install and invoke. What does it do? It is going to help you to describe the information according to some more descriptive statistics. But those descriptive statistics are they are quite a little bit different. For example, the confidence interval will be added. The variances will be added. The coefficient of variation, especially when you are dealing with non-parametric data. Non-parametric data, the coefficient of variation is important. So I deliberately decided to load that and generate this information. That's what you see here. Okay. So let's just take one of the variables. Okay. Let's take a variable like the log of wage. Okay. This one, the log of wage. So if you look at the log of wage, for example, it has more variables. The minimum is there, the maximum is there, the range, the sum, the median, the mean, the standard error of the mean, the confidence interval of the whole variable, variance, the coefficient of variation. It has all of this. So if you want some specific more variables, more descriptive statistics, okay, and in some cases, some descriptive statistics are very useful, then you use that. Okay. And then there is a library psych, which will also give you even more descriptives. Okay. This is a library psych. Run that. And when you run that, you do describe of the rich band data. That is this. That is beautiful. That gives you loads and loads of information. And once again, watch it. When you take a value like, I just want to take the log of wage. Look at that. If you take the log of wage, like the way I'm highlighting, it gives you more info. What info? It gives you at the top the mean, the standard deviation, the median, the minimum absolute deviation, the minimum, maximum, range. Okay. And then when you come down here, it gives you even more. It gives you the skewness, the ketosis, and the standard error. So all of this first preamble is just to tell you the descriptive information you can have. Okay. Sometimes you are dealing with groups. Sometimes you are dealing with foreign companies versus domestic companies. And you want to describe the information for only foreign companies and only domestic companies. Then you check the means. And then you want to check whether the means are significantly different from each other. Okay. You can do that. Even if the groups are 4, 5, 6, 7, 10 different groups, you can describe the wage band data according to groups. So this command will help you to do that. Okay. With all the packages you've already loaded, when you do describe by, so this one, it will describe according to year. And that one is very long, very, very long. So I don't want to do that one. So you can describe, remember the years are 1981 to 87. Okay. So the thing is that it's going to give you the information for each variable. Let's do it. Okay. Let's do it for you to just see. It's long, but then let's do it. So when you take a particular variable, like you take a particular year, say year is 1987. This is year 1987. The 1987 alone, you can now have the information for the data. So you can have the mean of every variable for 1987, the mean for every variable for 1986, and then on and on. Described by group by that time. You can also describe by marriage. So I want to classify those who are married and those who are not married. They are descriptives. So watch. When you do that, this is what you get. So you can see that when I go up, 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 you will see group yes. So those who are married, you get information about all of them. And the top one will be group no. Those who are not married, you can also get information about it. So the good thing is that you are able to get information across groups, and you can have several other more. Now, the next thing that I want us to look at, this is preliminary, we call it exploratory. Okay. The next thing that you want to be able to appreciate in your work, and by the way, I've done all of this command, is, let me just go back here. The next thing you want to do is you can look at the dimension of the panel data, the dimension. So this small command, PDIM, okay, once you run that, it will tell you the dimension. This is a quick thing. Okay, this is a quick thing where you're able to see that, oh, my data is unbalanced panel. Though the total sample size is 4660. Okay. Oh, the T is 1 minus T, and then the sample is 460. So it just tells you the dimension of the data. The dimension of the data. Just the dimension. Now, the next thing is an important thing to determine whether there is heterogeneity in the data set. Is there some form of heterogeneity in the data set? That is what this exploratory data analysis is going to reveal here. So the command called Coplot. Okay, I've got a question by someone. Grace. Grace, you ask your question.
No, please, why is it T1 minus 1?
It's a time. Remember, I told you that in this very context, it doesn't consider the time as that important.
Okay.
It doesn't consider the time as that important. So you just have it there. Okay. It's not too important. It's just to know that it doesn't consider the time as important. Okay. Now, the next thing you want to look at is the coplot. And this is important because it's going to give you watch the command, the log of wage, okay, by year, according to each particular individual, given each particular individual, okay. And on this data set, what it's going to do is that it's going to tell you the position of every single individual observation, every single one. But sometimes the results will not even show because there are quite many. Remember, my data set is over 4,000. So we pray and hope that it will show. Okay. And this will show IDs. You see a bar, okay, that will show IDs from the left to the right, starting on the bottom row. And I'm going to tell you why we do this, because it just helps you to see the nature of your data. Okay. So let's just run that command. This is just preliminary to see the nature of your data. Okay, so we do something. It says the figure is too large, so let's see. I just want to show you the graph. Okay, you can see that it's quite thick, It's quite thick. So look at that. There's a bar at the top. It just shows you the nature of your data and whether there are possible outliers. And you can see that the years are from 1980 to 1987. Those years of data are all shown in each graph. And when you look at the data, you can see that there is a bar that pops. There are some of the observations that pops away and then hits the bar, like this one here. It hits the bar. And so it just gives you a picturesque understanding of how thick your data is, how nucleated or scattered the data is. And in this context, I can see that they are quite nucleated or much more scattered. Okay. Now, normally exploratory analysis like this can reveal something to you. Okay. It can give you a fair idea of how this data actually looks like. All right, the next thing is a scatter plot of the data. This is just for the log of the wage. Okay, the log of the wage. I'm just going to do a scatter plot of the data. And like I said, this one might not show. The figure might be too large, it will not be able to show. And yes, it didn't show. Now let's go to the next one. This will check for heterogeneity across the observations, the workers. Okay. it's going to check for heterogeneity. Yeah, when it's so much, it doesn't show. When it's a lot. But I did it earlier and I had it, so I'm just going to show you that one. Okay. So this is what you will get. This is a heterogeneity across the workers. Now, if you look at this, and the beauty of what is happening here is that these are the number of observations from 30 all the way to, whatever that you have here. You have the individual workers on this axis there, and you have the log of the wage. This is a log of the wage for the first one, and this is a log of it for the second graph. Now, these graphs are telling you how the information is just nucleated in the middle there, and how some of the observations are like this one, are far away from the actual group of it. So we can see from here, okay, I can sense a little bit of information from here that there is some bit of heterogeneity. Okay? There's some bit of differences, okay, across individual workers. Okay? This is a heterogeneities across individuals, not across time, but across individuals. Okay, this is a heterogeneity across time. That's another graph you can do. And by the way, let me just show you this graph before. Okay, this is a heterogeneity across time. Let me run that here and see what happens. Sometimes it shows, sometimes it doesn't show. Okay. Sometimes it shows, sometimes it doesn't show. So you install. Okay. You install and invoke the library gplots. Okay, let's run this and see now. That is our graphic. And oops. Okay. Sometimes, like I said, you get some of the information, but the key thing is that they are showing now. Okay. So the library gplots, thank you for the. Oops. It will give you a bit of precise understanding. See, sometimes when you have some of these things and you are presenting them in a journal, they look nice. It just goes to show that you have done something. You know what I mean by you've done something. Like you feel like you've done something. Okay, let me just take myself back to the original. You feel like you've done something. Yeah, that's it. So that's it. There's a time dimension that you have there. And you can see, according to the time dimension from 1980 all the way to 87, you can see that the log of wage is going up. Okay, it's going up. Of course, the nominal wage will be rising, but we needed a real wage. And this one is telling us that the real wage is presumably also what? Also rising. So you can see clearly that it tells you that time may have an impact. This is the whole point. Time may have an impact on our results. And so we cannot ignore time. That's all it means. Okay. So these are the immediate information that you want to check before. That group may have an impact on the result, and time may have an impact on the result. And you can see that here. Okay. That in our own, the time is rising, like that. And this is the idea behind this time and group heterogeneity. Okay. So with that in mind, this is our pooled OLS that we had before. And we're going to now run the pooled OLS. Okay. And so I'm going to go to my R and then run this command. Okay. I called it W polls. W was for the wage pan, the wage. Then POLS, okay, pooled OLS. Then you use a PLM package. The log of the wage is a dependent variable. The dependent variable is your log of the wage. Then all of these independent variables, you capture every one of them, including the time dummies. Okay. Including the time dummies. So you have all of that there. Okay. Now, by the way, when you check the Excel, it is very important you appreciate it. If you check the Excel, this is the Excel. You can see that we included the time dummies from 81. Okay. Because the current year, the base year, 1980, wouldn't make any difference. So let's go to our R and then run this command. Okay. So the first command we are going to run is the pooled OLS. That's the first command, pooled OLS. Now this is a command, let me run that. And then here you go with the results. This is a result. This is a result. And this is a result. Okay. Now, the results will tell you something interesting. It was first tell you that the whole thing was pooling model. So you can see that it's a pooling model. It will also tell you your formula that you used, where the log of wage is a dependent variable, you know, and everything else as is shown there. It will tell you that this is the balanced nature of the panel. Your interesting thing you're looking for is this, the coefficient. Okay. So you have the estimate, which is a coefficient. You have the standard error. The estimate divided by the standard error will give you the t statistic of the t value. And then finally the probability, and then the level of significance are in stars there. We'll come and interpret this. At the bottom, you will see the residual sum of squares. The R square is 19%. The R square is 19%. Okay. And somebody might say that it's not good or it's good. It's good, depending on how you look at it. The adjusted R square is also 19%. Now, the F statistic shows a very significant p-value. Very significant p-value. So, what do all these mean? Well, we'll come to the interpretation of them. But the key point is that you've been able to run a pooled OLS on your work. So this is a command, and you can run the whole model without the year dummies too. But here we wanted to see the impact of time, the impacts of how time is affecting. And we'll look at that in the results. And you can see all of that here. These are the time dummies. So it tells you the impact. It tells you how wages are changing over time. That's all it means. And we'll come to interpret each one of them. All right. So first question we want to address here is which independent variable has the largest coefficient? We'll come back to address each one of these questions, okay, in our next video, because at this stage, I want to take my time to walk you through one by one the content of this. And remember, the only one we've run is the pooled OLS model. We'll look at each of the coefficients, interpret all of the results before we go into the other models.